Hello everyone, my name is Ding. The topic of my talk is chaotic evolution algorithm in combinatorial optimization for solving travel salesman problem. This is the outline of my report. The term chaos was first proposed by Chinese-American mathematician Li Tianyan and American mathematician James York in 1975. Li published an article titled 3 Implies Chaos in Mathematical Monthly and given a mathematical definition of chaos, which is now called the Li definition. Since then, chaos has been given a scientific concept and has become a scientific term. In Li Tianyan's article, the following equation is used as an example to discuss the output of the system when mu take different values. As shown in the figure, the x-axis represents the value of mu, the y-axis represents the output of the equation when n tends to infinity. When mu is set to a value from 0 to 1, the price point of the system is 0. The system output tends to 0. When mu is set to a value from 1 to 3, the price point of the system is equal to 1 minus the negative power of mu. The system output tends to 1 minus the negative power of mu. When mu is set to a value from 3 to 4, as the value of mu becomes larger, the price of the system begins to bifurcate. When n tends to infinity, the output of the system tends to the price point. When mu is equal to 4, there are infinite price points and the system enters a chaotic state. Captures the system outputs of logistic map parameter mu is set to 1, 2, 3, and 4. The initial value is set to 0.7. When mu is set to 1 and 2, the system becomes stable and convergent. When mu is set to 3, on a small scale, the system shakes. However, on a large scale, it becomes convergent and stable. When mu is set to 4, the system results in chaos. The chaotic evolution algorithm is a population-based optimization algorithm. When a chaotic evolution algorithm is used to solve the problem of the continuous domain, the algorithm used a Gaudi state of chaos to realize the search in the whole space. Chaotic evolution algorithm introduce a mathematical mechanism in the iterative evolution process and simulates the traversal motion in the search space with a simple principle. Generating chaotic vector is a key operation of chaotic evolution algorithms. The target vector is used to generate a mutant vector to simulate the chaotic motion in the simulated search space. By crossing the target vector and mutant vector, a chaotic vector is generated. In equation 1, di is the direction factor, and di can take a value of 1 or negative 1. CPI is a chaotic parameter. The initial value is set to a random number in 0 to 1, and it is updated with the iteration of the chaotic system and proposed a new control parameter, direction factor ratio, DR, used to control the percentage of positive and negative in DI to guide the chaotic evolution algorithm search direction. And DR equal to 0.7, it means that 70% of DI is 1 and 30% is negative 1. Suppose that an array on the left side of a figure means individuals. Contour lines at the right side are the fitness landscape, and the circles on the landscape are individuals. The vector is searched in the whole space through mutation and crossover under the control of the parameters. Until a satisfactory solution is found, all the algorithm research the maximum number of iterations. The program stops running and outputs the optimal solution. We chose taboo search algorithm and simulated annealing algorithm as a comparison algorithm. On the left are the iterative steps of the taboo search algorithm, and on the right are the iterative step of the simulated annealing algorithm. The traveling salesman problem is a well-known discrete problem, representative combinatorial optimization problem in a graph theory, and an NP-hard problem. The solution to many practical problems can be transformed into the solution of the traveling salesman problem. For example, the operation of the train, the route of the carrier to deliver the express. Therefore, the solution to the TSP problem has always been highly valued. The TSP is a classical combinatorial optimization problem. The classical TSP can be described as a merchandise salesman who wants to go to N cities to sell merchandise. The salesman starts from one city to need to pass through all the cities before returning to place of departure. How should the travel route be chosen to make the total travel the shortest? As shown in the figure, the points in the three graphs are the city point positions in the TSP problem for 100 cities, 128 cities, and 734 cities. The principle of the chaotic evolution algorithm is to simulate to traversal motion of chaos to realize a global search and generate the mutation vector through the processing of the previous generating of vectors. As shown in the figure, the positions of mutations are generated by chaotic sequence. For example, two positions 2 and 7 are selected. Exchange the city number corresponding to the position of the sequence A to obtain A' mutation vector. The crossover process is shown in the figure. First, the crossover position is determined by the chaotic sequence. For example, we selected the 3rd and 7th positions. Then we place the selected number in A in front of the B sequence, generates the B' sequence. Put the selected number in B before the A sequence to generate the A' sequence. Finally, we delay the second occurrence of repeated numbers from front to back in A', B', and generated crossed vectors A double prime, B double prime. As mentioned above, we proposed a chaotic evolution algorithm, and the following description outlines the main step of the implementation of the chaotic evolution algorithm. Step 1. Initialization. Step 2. Generate the initial solution. Step 3. Fitness calculation. Solve the objective function of each individual to obtain the fitness value of the individual. Step 4. Crossover operation. Step 5. Mutation operation. Step 6. Judgment operation. The three pictures from left to right are the city connection maps obtained when the taboo search algorithm processed the three TSP problems. It can be seen from the figure that the taboo search algorithm fails to converge to the global optimal solution in a limited iteration process. The three pictures from left to right are the city connection maps obtained when the simulated annealing algorithm deals with the TSP problems. It can be seen from the figure 9. The results obtained by the simulated annealing algorithm are similar to tabu search algorithm, and it fails to converge to the global optimal solution in a limited iterative process. The three pictures from left to right are the city connection maps obtained when the chaotic evolution algorithm processed the three TSP problems. It can be seen from the figure 9. The chaotic evolution algorithm successfully converts to vicinity of the global optimal solution in a limited iterative process. As shown in the figure, the results obtained when the three algorithms deal with the TSP problem with the number of cities of 100. The broken line in the figure represents the change process of the current optimal solution as the number of iterations increase during the operation of the algorithm. From the line chart, we can see that in the iterative process of the chaotic evolution algorithm, the current optimal solution changes much faster than the simulated annealing algorithm and tabu search algorithm. The current optimal solution of the chaotic evolution algorithm quickly converts to the global optimal solution. However, neither the simulated annealing algorithm nor the tabu search algorithm converts to the optimal solution in a limited iteration process. As shown in the figure, the results obtained when the three algorithms deal with the TSP problem with the number of cities of 128. As shown in the figure, the results obtained when the three algorithms deal with the TSP problem with the number of cities of 734. From the above three broken line graphs, we can all get the same conclusion. The result of the chaotic evolution algorithm is significantly better than the other two comparison algorithms. After running each algorithm 30 times, we compared the algorithm, chaotic evolution algorithm with the simulated annealing algorithm and the tabu search algorithm. Through the significance test, the p-value obtained by the comparison between the chaotic evolution algorithm and the other two algorithms is less than 0.05. When the significance level is alpha equal 0.05, the operating results of the chaotic operation algorithm are significantly different from of the simulated annealing algorithm and the tabu search algorithm. In this study, we use a logistic map to generate a chaotic sequence. The logistic map has the characteristic to uneven traversal. Therefore, next, we will consider whether to use time map, Q map, logical self-mapping, and other more evenly ergodic mappings to generate a chaotic sequence, and whether we can get better results. That's all. Thank you for listening to my report.